Let us now move to optimization. We will figure out what is optimization through problems. But basically, if I were to give you a short definition, in such type of problems, we are either trying to maximize or minimize anything. It might be maximize or minimize the profit, the area of something, the volume. And this is why in this chapter, knowing area and volume formulas will be important for you. And at the end of this chapter, so at the end of chapter 7, I will be giving you a list of some common volumes for you to know. So these 6 steps are 6 steps found in your book, which are just a few like strategies, or maybe this is a few steps for you to follow in order to for you to be able to easily and to solve these problems in an organized way. So step one is understand the problem. Basically, read it. Read everything in the problem. Make sure you understand the English, what they are saying, and make sure that you understand the problem. Even if solving it might not be very clear at this stage, just make sure you understand what's happening. Then draw something. Drawing always helps. Don't get fooled and say to yourself that drawing is a waste of time. No, this is false. Drawing always helps. So draw something for yourself. And then in part three, introduce a notation. So maybe like introduce a variable. Let's say if you're working with area, you can use A. If you're working with length, you can use L. The variable itself does not matter what letter you use, but you have to introduce some letter to work with. And in step three, you would have expressed, let's say, area is like length times width. You would have expressed it in the terms of two variables. What you want to do in step four is make this expression in the terms of one variable. You will understand this more in the following examples that we will do. But in part five, you need to use so if q has been expressed as a function of more than one variable in step 4, use the given information to find relationships in the form of equations among these variables, then use these equations to eliminate all but one of the variables in the expression for q. Thus q will be expressed as a function of one variable x. Say q equals to f of x. Write the domain of this function in the context. So, in other words, we have made this function in the term of one variable, and you want to know what the domain of this function is when it can exist. Finally, in step 6, as I said, in these problems, you're either trying to maximize or minimize something. So you need to find either the absolute maximum or minimum value. This can happen either through first derivative test, second derivative tests, or it can happen by other ways. Usually we will use the easiest thing to go to is the first derivative test. However, at some points we might use the closed interval method, uh, which, if you remember, if we had an interval, we would compute the value of the function when the derivative is zero. So let's say we have f of x and we have the derivative of f of x. So we set the derivative to be equal to zero. So let's say the derivative is equal to zero at point A. We find what is f of a, and then we also find f of the endpoints of the interval. So if the interval is from c to d, we find f of c and f of d, and we check which one is the highest one, which one is the lowest one in here. So again, don't worry about this. We will look at these different methods. In different problems, one of the problems we'll use the closed interval method, and another we will use the first derivative test. So let's start. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? First of all, try to understand what's happening. We can understand through drawing. So you have a river. I drew it in blue. and you want to make a fence. So if you fence on three sides, but they said that the river needs no fence along it. So it's only a fence made up of three sides and not four. So, and this makes a rectangle, except you don't use the last side. So you only have three sides. So what are the dimensions of the field that has the largest area? I just wanted to show you that we can have many options. So let's say these sides are 100 and this one is 2200. They all add up. So if we do 2200 plus 100 plus 100, this gives us 2400. And the area is the width times the length. So 100 times 2200, which is 220,000 feet squared. However, this is not the only option. We can have a lot of options. What if this was 700 and 700 and this was 1000? Again, they all add up to 2400 because 1000 plus 700 plus 700 is 2400 feet. And the area is 700 times 1000, which is 700,000 feet squared. So we can have a lot of options. And in this problem, we would like to find the option that maximizes the area. So I was just explaining above, you do not have to include what I wrote above in your answer. I will show you what to include. So if you were writing your answer, make sure to draw a general drawing. Where this is the river, you can call this side X and this other side Y. So then we will use the variable a because we're finding area. So a is x times y. Now one thing to notice that if you add up all of these sides, so if you do x plus y plus x, what will this give you? You have a total of 2400. So adding them all up will give you 2400. Why am I doing this? Because now that we know this, we can try to solve for y in terms of x or x in terms of y. So let's say this becomes 2x plus y equals to 2400. So we can solve for y in terms of x and we get 2400 minus 2x. So now that we know we expressed y in terms of x, what we can do with this is that we can express the area in terms of only one variable. So instead of writing xy, instead of the y, we can write 2400 minus 2x. Let us expand. This gives us 2400x minus 2x squared. So now we have area in terms of one variable. Now I just wanted to point out, since area is in terms of x, we can write it a of x equals to 2400x minus 2x squared. So as in the steps earlier, we said that now we should find the domain of this function. So over what values of x does this function exist? Now let's think to ourselves, what can x be? So if we add up all of these three sides, if we add them all up and we get 2400, what can the maximum value of x be? Keep in mind that x is available on both sides. So if the maximum of 2x might be 2400, then the maximum of x would be 2400 over 2, which is 1200. So this is the maximum value x can be. And of course, x cannot be negative. So we can say that 0 is less than x is less than 1200. Of course, you can also write this using interval notation. It does not matter. So now that we know the domain, we would like to, what did the question ask? The question wants to maximize the area. So again, of course, in order to try to maximize something, we would first like to find the derivative. So let's find the derivative of a of x. This will give us 2400 minus 4x. In this problem, we will first set the derivative to be equal to 0 in order to find the critical points. So if we set it equal to 0, let us solve for x. Negative 4x equals to negative 2400. So x equals to 2400 over 4, which is equal to 600. And we know that x belongs to 0 till 1200. So now let us find the value of the function evaluated at each of these points. So first we find a of 600, which is a critical point, and we find a of 0 and a of 1200. So what is a of 600? If I were to plug in 600 in the function of a of x, this will give me 2400 times 600 minus 2 times 600 squared, which is equal to 720,000 feet squared. A of 0 is equal to 2400 times 0 minus 2 times 0 squared, which is 0. And a of 1200 is 2400 times 1200 minus 2 times 1200 squared, which is also 0. So in these three values that we got, the maximum one of these values is 720,000. So we can conclude and say the maximum area is 720,000 feet squared. Let's see if the question asks for something else. The question asks for the dimensions of the field that has the largest area. So we technically did not answer the question. The question does not ask for the maximum area. But now that we know that this is the maximum area, at what x value does it occur? It occurs when x equals to 600 and y equals to. So above we found that y is equal to 2400 minus 2x. So this is 2400 minus 2x, which is equal to 2400 minus 2 times 600. And this gives 1200. So we can conclude and say the dimensions of the, what do they ask for? The dimensions of the field that has the largest area are 600 feet and 1200 feet. So now let us move to another problem. We have a cylindrical can. It is to be made to hold 1 liter of oil. So this can that you see right here, it can hold 1 liter of oil. We would like to find the dimensions that will minimize the cost of metal to manufacture the can. So how do we do that? Again, step one, try to understand what they're asking. Even if solving the problem might be hard, just try to understand what they're asking. We would like to minimize the cost of the metal to manufacture the can. What does this mean? This means that we want to minimize the area, because less area, smaller area means less metal required. Now, how do we do that? We start by defining the area. What is the area, as we did in the previous problem? So area, now what is the area of a cylinder? You see this figure right here, figure 4. You see that they first start by showing you that the area of a cylinder is 2 times the area of these disks because we have one on top and one on the bottom, and the area of everything in between these disks. And to find the area of everything in between these disks, it's 2 pi r times height. So the total area, we add them both up. So it's 2 pi r squared plus 2 pi r h. Now we have two variables in here. Here it's a tiny bit tricky to solve to find a in terms of one variable. So how do we do it? So you might notice that in the question they told us that the can is made to hold 1 liter of oil. And you might know that 1 liter in fact is equal to 1000 centimeter cubed. So how does this help us? This this means that the volume is 1000 centimeters cubed. Now, what is the volume of a cylinder? It's pi r squared h. So pi r squared h is therefore equal to 1000 centimeter cubed. Now we can solve for one variable in terms of the other. Maybe in this case it's easier to solve for h in terms of r. So h is equal to 1000 divided by pi r squared. Now we plug this in to a, so we get a equals to 2 pi r squared plus 2 pi r times 1000 divided by pi r squared. Overall, this gives us 2 pi r squared plus 2000 divided by r. So now we can actually write this as a of r because a is only in terms of r in here. So now let us find the domain. What can r be? We know that r cannot be negative, it has to be positive. So r is greater than 0. But we actually don't have a maximum value. So maybe this is enough for here. So even if we don't have a maximum value. So what can we do moving on? Moving on, we can find the derivative of r and try to minimize it or maximize it, depending on the question. So in this question, we would like to minimize it. So let's find the derivative. So the derivative of r is equal to 4 pi r minus 2000 over r squared. Let us put a common denominator. So we get 4 pi. If I multiply the numerator by r squared and the denominator by r squared, I get 4 pi r cubed minus 2000 divided by r squared. And now we can even factor the 4. This gives us pi r cubed minus 500, all divided by r squared. Now, let us solve this derivative equals to 0 as we did before. So if we solve the derivative equals to 0, this means in a fraction, it's always the numerator that's 0 of the fraction that is 0. So, of course, 4 is not 0, so pi r cubed minus 500 is 0. So r cubed is 500 over pi. So r is the third root of 500 over pi, or the cubic root of 500 over pi. Now, what can this help us with? Because we just found r, which is 500, the cubic root of 500 over pi. This value is when the derivative is 0, so this is what we call a critical point. We can now use the first derivative test. So, let us look at what a is when r is less than the cubic root of 500 over pi, and when r is greater than this value. So let us draw a table. So again, let's look up and check what a is. A is 2 pi r squared plus 2000 divided by r. So I will write it on the side here. A is 2 pi r squared plus 2000 divided by r. So here I will write a. Uh, Here I will write the derivative of a. And here I will write a, or we can just state whether it's increasing or decreasing. And of course, r is between 0. R is not 0. It can be above 0. It can be 500 over pi, the cubic root of this. It can go up to infinity. There is no max point. So I just wrote that r is above 0. And now let's find the derivative when r is below the cubic root of 500 divided by pi. So the function for the derivative is 4 pi r cubed minus 500 divided by r squared. Notice that when r is less than the cubic root of 500 over pi, the derivative is negative. When r is greater than this value, the derivative is positive. And the derivative is 0 at this value. This means that the function is decreasing and then increasing. What does this tell us? This tells us that at this value here of r, we have the absolute minimum. So we can write this down, absolute minimum at r equals to cubic root of 500 over pi. Now what we do now is we reread the question. What is it asking? It's asking for the dimensions that will minimize the cost. Dimensions means the r, like what is r and what is h. We found r, and now we already know what the function, what h is in terms like how to find h in terms of r. We found this before to be 1000 divided by pi r squared, as you might remember. We did it here. So we use it to find what h is. This is 1000 divided by pi. Now in here we plug in r. R is 500 divided by pi, the cubic root. We can write the cubic root as 1 over 3, and all of this squared, which is 1000 divided by 500 divided by pi to the power of 2 over 3. You can leave it here. You can continue simplifying. I just wanted to let you know that if you continue simplifying, you will get 2 times the cubic root of 500 over pi, which is 2r. So the dimensions of the cylinder that will minimize the cost of metal are r equals to cubic root of 500 over pi and h equals to 2r. We will now move to another problem. So in this problem, it's a bit different from the other ones. Here we are working with a given function. We're trying to minimize distances. So find the point on the parabola y squared equals to 2x that is closest to the point 1, 4. This is 1, 4. We want the point that is closest to it. How do we do that? First, as we did before, we define a function. In this case here, our function would be the distance. How do we find the distance between 2 points? If you remember, we do x1 minus x2 all squared. So in this case, x minus 1 all squared plus y2 minus y1. So y minus 4 all squared and the square root of all of that. Now we would like to either solve for x in terms of y or y in terms of x. In fact, this is already given because we know y squared is equal to 2x. We either solve for x or solve for y. I will solve for x because it is easier to solve for, so x is equal to y squared over 2. Now we can plug this in. So if x is y squared over 2, we can write y squared over 2 minus 1 all squared plus y minus 4 all squared. The square root of this is the distance, And we can, since it's now expressed in only the terms of one variable, we can write this as d of y. Now, one thing to point out is that now we would like to minimize d of y. So we can take the derivative and then use the first derivative test. But just one thing I wanted to mention is that minimizing, or the value that minimizes d of y, the value of y that minimizes d of y, which is y squared over 2 minus 1 all squared plus y minus 4 all squared, is the same value as the one that minimizes d squared. So d squared is y squared over 2 minus 1 all squared plus y minus 4 all squared. So we can simply square d and find the value that minimizes it. If you did not notice it, if you continued working with the square root of all of that, it does not matter. It is not wrong. It's just that this will take you more time. But for now, I will square d, and I will define a new function. Let f of y equals to d squared, which is y squared over 2 minus 1 all squared plus y minus 4 all squared. Now, as we did before, we find the derivative. The derivative is 2 times y squared over 2 minus 1, and multiplied by y plus 2 times y minus 4. If I were to simplify it, it gives y cubed minus 8. And then we set the derivative to be 0. So if we set the derivative to be 0, y cubed minus 8 is 0, so y cubed is equal to 8. This gives me y equals to 2. What I do with this is the same as what I did in the question before it. So this is the derivative, and this is the function. So I can go from negative infinity to 2 till infinity. Note that in this question, we don't have any restrictions on the domain because we are looking for like in which values can y exist. And notice that the range of this function is all real numbers because it will keep on continuing. It will actually cover all real numbers in the range. So y can be anywhere on all the reals. However, if you happen to be working with x, so if you solved y in terms of x and plugged it in and worked with x instead of y, you would have been able to say that x is greater than 0, or greater than or equal to 0. But y in this case belongs to all real numbers, and we are working with y. This is why I went from negative infinity up to infinity. So you might notice that the derivative is negative in the interval negative infinity till 2. It's 0 at 2 and positive when y is greater than 2. Therefore, the function is decreasing in the first interval and then increasing, which shows that at y equals to 2, we have an absolute minimum. So again, let's go back to the question. The question actually asks for the point that is closest to 1, 4. The point has x and y coordinates, so we also need the x coordinate. And we already solved that x is equal to y squared over 2. So we use this to solve for x. Therefore, x is equal to 2 squared over 2, which is 4 over 2, which is 2. So the coordinates are 2, 2. These are the coordinates of the point on the parabola that is closest to the point 1, 4.